Today, we're going to circle back to analyzing experimental data. Specifically, we're going to investigate a more sophisticated technique to find the relationships between the dependent and independent variables in experimental data. If you recall from what we did back in grade 11, we were doing what I would refer to as the multiplier method. And this is where we would take a look at the actual data set and simply do division. So we'd look at the multiplier between the second and the first data point. So 4 divided by 2 on the independent variable. Then we did 200 divided by 100. And of course, when we wanted to figure out the next one, it was the third divided by the first on both sides. And then of course, we get our multipliers here. The obvious flaw with this technique is really based on the quality of the data itself. Experimental data always will have error in it. And because it has error, these multipliers will sometimes not be perfectly aligned. So then there's a bit of guesswork. We have a much more robust technique now that takes the guesswork out of it. But to do it, we have to know a little bit about something called logarithms. A logarithm is just an alternative way of expressing a power. And logarithms work with any type of base. We're going to start with the most common one, which is base 10. So let's talk about the idea of what this is all about. So let's say we have the number 100. The question is, what power of 10 will produce 100? Well, the answer to that question is 2. So most of us are already familiar with this. And let's do something equally as easy. 1,000. Well, that is going to be 10 to the exponent 3. Logarithms find an alternative way of expressing this in a different type of notation. So let's take a look at what I mean by this notation. So let's say we have y equals, let's maybe not use the cursive y is equal to log 100. Now, you actually already know the answer to this question, and the answer is 2. So what this says and how this notation here is related to what we did over here, I will do my best to explain. When you see this expression here, and you just see the word log, that assumes that we have a base of 10. And how this reads is as follows. What exponent of 10 produces 100? So the other way to write this is as follows. 10 to what exponent y will produce 100? And obviously the answer is 2. Now let's try another example. Y is equal to log 10,000. Well, if you were to type this in your calculator, you would get a value of 4. Because really what this means is what power of 10 will produce 10,000? So again, this can be rewritten in the following notation. 10 to the y is equal to 10,000. And easily enough, we could convert this into a power of 10, which is 10 to the 4. So y is equal to 4. Just so we understand the notation, we're going to go through some more examples just to understand what this terminology means. Now, let's take a look at our first sample problem here. Sample problem A. Now, in this case, what you're going to notice is that we're talking about a different base this time. Instead of base 10, this is base 3. So we're trying to find the log base 3 of 9. Well, let's convert that into the notation I showed you before. The other way that this could be written is this. Y equals log 3, log base 3, I should say, of 9. So translating this into notation that you're more familiar with is 3 is our base. So what exponent y produces a 9? And the answer is 2. 3 squared equals 9. So our y value is equal to 2. Let's take a look at our second example. In our second example, our base is 4. So what exponent of 4 will give us 16? So 16 equals 4 to what power of y? Most of you probably recognize that 4 squared gives you 16. But the other way you could do it too is you could rewrite 16 as 4 squared. And then we just focus on the exponents. Y is equal to 2. And simple as that. Okay, so let's take a look at this one. So this one, 2 equals log base 3. So 2 log base 3, and we're trying to solve for x. So again, as a reminder, what this means. On this side, this is our exponent. And the 3, that would be our base. All right? So our base is 3. Our exponent is 2 equals x. Okay. Well, not terribly challenging, I should say. X equals 9. Very straightforward. But again, things start getting a little bit more complex. So let's take a look at the next one here. So we want to find log base 9 of 1 over 9. So let's translate that into better notation. So y equals log base 9 of 1 over 9. All right, so now let's get this into a more familiar notation. So this will be 9 to the exponent y is equal to 1 over 9. Now, if you recall, 1 over 9 is just the same as 9 to the negative 1, because 1 over 9 is a reciprocal, which is 1 over 9 or 9 to the negative 1. Well, therefore, y must be equal to negative 1. And once again, why do we have negative exponents? These are always good things to review. Let's say we have 100 over 100,000. Okay, well, there's a couple of ways that we could simplify that. So this would be the same as, we could just cancel out a couple of zeros. And if we do that, we get 1 over 1,000, which is equal to 1 over 10 cubed. Or we could do it this way. 100 is the same as 10 squared, and 100,000 is the same as 10 to the 5. And if you recall, when you have the same base and you're doing division, you subtract the exponents. This gives us 10 to the negative 3. So therefore, 10 to the negative 3 is the same as 1 over 10 to the 3. Or in general, x to the negative n is the same as 1 over x to the n. It never hurts to review. Moving on, let's check out sample problem E here. So y is equal to y equals log base 10 of 0.1. Okay, so let's put it back into the more familiar notation. So 10 to the exponent y equals 0.1. Well, let's try to express 0.1 as base 10. Well, 0.1 is the same as 1 over 10, which is equal to 10 to the negative 1. Therefore, y is equal to negative 1. Pretty simple. Next, part F. Okay, so now our base is 5. So 5 to the y is equal to 5 to the power of root 3. Okay, jokes. This one's much easier. Therefore, y is equal to square root of 3. And that's the thing. Sometimes the notation looks harder than the actual math is. And part H, we want to find y. Our base is 4. So we are trying to figure out what power of 4 will give us the square root of 2. 4 to the exponent y is equal to root 2. Our problem here is that our bases don't match. So what we're going to do is we're going to get it so that the bases do match. Well, first of all, 2, square root of 2, I should say, is the same as 2 to 1/2. Now, 4 can also be expressed as a power of 2. So 4 is the same as 2 squared and then to the exponent y. Well, when you have an exponent of an exponent, you multiply them. So this becomes 2 2y is equal to 2 to the 1/2. So now we can solve for y. So we know 2y has to equal 1/2. Therefore, y is equal to 1 over 4. Awesome. So there's a little bit of familiarity, hopefully, with how logarithms work. Next step, though, is we have to talk about the specific logarithmic rules. There are 6 of them. Our first rule is a product rule, the log of products. So the log of n times m is equal to the log of n plus log of m, and of any base. This works for any base. Let's do a mathematical example to highlight this one. So I'm going to do the following. Left side, I'm going to say the log of 100 times 1,000. And on our right side, that should be log of 100 plus log of 1,000. When we write log by itself, without anything underneath it, that is assumed to be base 10. Okay, so let's actually work out the math here first of all. So this is the same as log of 100,000. So what exponent of 10 gives us 100,000? Well, 1, 2, 3, 4, 5, 10 to the 5. Now let's take a look at the right-hand side. Log of 100. So what power of 10 gives us 100? Well, that's 2. And what power of 10 gives us 1,000? 3. And I'm sorry, I apologize. I'm conflating power and exponent. I meant what exponent of 10 gives you 100 and what exponent of 1,000 gives you, what exponent of 10 gives you 1,000, and that is 3. Anyway, 2 plus 3 equals 5. And actually should fix this notation because it's not 10 to the 5. Sorry, the answer would just be 5 because log is asking for what exponent. What exponent of 10 gives us this is 5. Awesome. Next, the quotient rule. And this one states that the log of a quotient is equal to the log of the numerator minus the log of the denominator. So let's look at a sample problem of this variety. So on the right side, let's say we have log of 1,000 divided by 10. And apparently, I can't tell the difference between my left and right. How about left side? There we go. The right side should be log of the numerator, which is 1,000, minus log of the denominator, 10. All right, well, let's simplify the left-hand side. So that's going to be log of 100, I should say. And what power of 10 gives us 100? The answer is 2. Now on the right-hand side, log of 1,000 is 3 because 10 to the exponent 3 is 1,000, and 10 to the exponent 1 is 10. 3 minus 1, we have 2. Now for the third rule, and this is the log of powers. So when you have a log of a power, it is the equivalent of taking that exponent and bringing it out front and multiplying. So let's do this example. So log 10 to the 4 should be the same as 4 times log of 10. Well, the log of 10,000 is indeed 4, which should be fairly obvious by that. And on our right-hand side, this is going to be 4 times, well, what exponent of 10 gives us 10? That's just 1. 4 times 1, that's 4. Rule number 4. The log of 1 is always going to be 0, no matter what base. This one, we can even look at a more generalized one. All we're going to do is we're just going to convert this to the other notation, the more familiar one, and this will make more sense. Because remember, this is actually the exponent on that base. So this says a to the exponent 0 equals 1. And that is always true. And it doesn't matter what base it is. If we have to the exponent 0, we always get the answer 1. And in case you forgot why, let me show you. Let's take 100 divided by 100. Well, 100 divided by 100 is obviously just equal to 1. But it also can be rewritten as 10 squared divided by 10 squared. Well, when you divide powers of the same base, you subtract the exponents. So that's going to be 10 squared minus 2, which is 10 to the 0. So 10 to the 0 equals 1. And in fact, that works for any base. So we could have 17 to the exponent 200 divided by 17 to the exponent 200. Well, we know that is equal to 1, or 17 to the exponent 200 minus 200, 17 to the 0. So the log of 1 always gives us 0 because any base to the exponent 0 will give us a 1. And then finally, the log of 0 is undefined. And here's the reason why that is. So let's just do the natural log, not the natural log, sorry, the log base 10. So when we do this, this is asking what exponent y will produce a 0. Well, that's actually impossible. It's impossible to do that. Now, y, to get close to 0, we have to start working with the negative exponents. So we can approximate it and get closer to watch the trend. So what if y is equal to the exponent negative 1? Well, that would give us 0.1. Y is equal to negative 2. That would give us 0.01. Y equals negative 3. I think we can all see where this is going. As the exponents become more negative, our answer approaches 0, but it will never reach it. So the larger, or I should say, the smaller the exponent is, the more negative it is, the closer to 0 we get. So really, y has to approach negative infinity to make this happen, to get it close to 0. So the next step is to explain how using logarithms can help us find the proportional relationship in our data. And that's what we're going to take on next. Many relationships in physics come in this form. Y is equal to some constant of proportionality times x to some exponent n. So for example, y is equal to 2x squared. So this would be a function that goes through the origin. The 2 would represent your a value, and the squared would represent your n value. Here is the kinematics formula for displacement, assuming that our initial velocity is rest, reduces down to d is equal to 1/2 at squared. Technically, it's d is equal to v1t plus 1/2 at squared, but assuming from rest, we can drop that. So in this particular case, the 1/2 times acceleration represents the a value, and the 2, your n value. And there are many examples of this. A is equal to pi r squared. Pi is your a value. The squared is your n value. Let's focus on that function. Y is equal to ax to the exponent n. Well, in math, we can do whatever we like mathematically to the left side of the equation so long as we apply that same change to the right side. So for example, if I wanted to, I could multiply both sides of the equation by 4. As long as both sides are multiplied by 4, it still works. Or if I wanted to, I could add 2,000 to each side. So long as whatever I do to the left-hand side, I do to the right-hand side, then we're good. But this isn't just limited to addition, subtraction, multiplication, and division. Other things too. So you could take the sine of both sides, or the cosine of both sides, or the square root of both sides. It doesn't matter. In this case, what I'm going to do is I'm going to take the log of both sides. So I'm going to get log y is equal to log bracket ax to the n. So the first thing we're going to look at here is that we actually have the product rule, because this is really a times x to the n. So we can rewrite the right-hand side of our equation to look like this. Log a plus log x to the exponent n. And then here we have the exponent rule. So then we can take this n and then bring it out front like that. So this gives us log y equals log a plus n log x. The next step is I'm going to swap the order of these two terms. This gives us log y is equal to n log x plus log of a. What's fascinating about this is really in a more familiar form than you realize. If you look carefully, this is analogous to our y term. The n acts like our slope. This basically is our x term, and this is your y-intercept. By using logarithms, we are effectively converting any relationship, whether it is linear or nonlinear, direct or indirect, into a simple straight line. And that's the fascinating power of using logarithms. These, when using a type of graph paper known as logarithmic graph paper, will generate straight lines no matter what the relationship is. And that is a very, very powerful tool. Now, of course, with modern computing, the software can actually extrapolate what the equations are. But this is an old school by hand method of solving these things when you don't have a computer algorithm available to you. So basically we have this as the y is equal to mx plus b form. So the thing that looks like our slope represents the exponent on our relationship. And the thing that looks like our y-intercept, our value for a, that gives us our constant of proportionality. So how do we use these in order to get the n value and the a value? Well, best practices is you need a minimum of 2 points. But generally speaking, I work with 3 points. We need 2 points minimum to calculate the value for n. And technically, minimum, you need 1 point to calculate the value for a, but it is best practices to use multiple points to calculate your value for a, and then take the average of those points. So here is the big idea. So let's start off with 3 theoretical points. So point A is x1, y1, point B, x2, y2, and point C, x3, y3. So we're going to find n using point A and point B. So our first equation we're going to use point A. So basically, using this equation here, we're going to substitute in for our values for y and x. Now, of course, since we're just working with the general case, and I should probably put those 2 points there, we write it like this. Log y1 is equal to n log x1 plus log of a. And that is our equation 1. And we're going to find equation 2 by using b, which is x2, y2. And then, of course, label it as equation number 2. The next step, just like good old grade 10, we're going to use elimination. And we're going to subtract equation 1 from equation 2, which gives us log y2 minus log y1 equals n log x2 plus log a minus bracket, very important, log x1 plus log a. So the left side, we'll leave that as is for now. And on the right side, we're going to clear the brackets. And hopefully what you noticed is that this positive log a will be canceled out by this negative log a, which is perfect because that gets rid of one of our unknowns. And I realized I made one small little mistake. I forgot the n here and the n there. There we go. Okay, so the next step, what I'm going to do is on the right-hand side of the equation, n is common to the 2 remaining terms. So we get log y2 minus log y1 is equal to n bracket log x2 minus log x1. Now to isolate for n, I will take the bracket log x2 minus log x1 and divide both sides of the equation with it. So we get log y2 minus log y1 divided by log x2 minus log x1 all equals to n. Let's turn that around. And here I'm going to cheat. Just copy and paste. OneNote's kind of awesome for that. Okay, and I forgot a subscript. Yes, subscript 1, bad human. Okay, there we go. Now, there's a simpler form that we put this formula in. But the reason why I'm leaving it and pausing at this moment, because if you recall, this value for n, and let's go back over here to the original equation. There we are. This value for n looks like a slope. And if you remember, the formula for slope is m for slope is equal to delta y over delta x, which is y2 minus y1 over x2 minus x1. And you should be able to see the similarity. Basically, the n value is just the log of the slope equation. So you already know the slope equation. All you have to do is put log in front of each of the variables, y2, y1, x2, and x1, and that is how you can solve and find the n value. No proportional reasoning required, no multiplier method, just this. Very simple. So this is the equation to find the n value, and you only need 2 points. The thing to consider though, we are still working with experimental data. So when you're working with experimental data, or data, whatever you prefer, you're still going to get error. But the thing is about the n values, in most relationships, especially at the high school level, the n values are going to be one of these values in this list. Note, your n is going to be equal to plus or minus 1, 2, 3, 4, etc. So your n value is either going to be a plus or minus of 1, 2, 3, or 4, or plus or minus 1/2, which is a square root, 1/3, cube root, 1/4, fourth root, etc., etc., etc. So what you do is based on your calculation, you round the n value you get here to the closest one of these. So if you got n is equal to 0.9899, you would round that to a 1. Or let's say you got negative, let's do that, negative 0.2435, whatever, something like that. That is closest to a negative quarter. So you would round it to negative 1/4. And the other thing that is important to note is you use the rounded value of n for your next step. All right, so the next step, of course, is we have to determine what the a value is. So now that you have your value for your n, we then go back to the original equation. This means to find a, use the original equation, or at least the original equation form, y is equal to ax to the n, but this time using the rounded version for your n value that we just found. So then what you're going to do is you're going to isolate for your a value. So we're going to get a is equal to y over xn, x to the n, whatever that n value was. And we're going to use all 3 points to calculate a, and then take the average of those 3 values. So you set it up something like this. I like to do things in chart form. So in the first time, we're going to find a1, our first version, using point A, and you'd write the actual values of the coordinates. So you start off with our formula. a1 is equal to y1 divided by x1 to the n, and then you do all your work, and then your little therefore a1 equals whatever it is, and then you do the same thing for the other 2 points. And that's what it would look like for B, and that's what it would look like for using point C. The last remaining step would be to find our overall A value by taking the average of all 3. And that would look something like this. A is equal to A1 plus A2 plus A3, all divided by 3, whatever that equals. And then finally, you would write your final equation as therefore y equals, and I'll do this in red, A, assuming that would be some value, x to whatever value of n that we got. Now, you're not always going to be using y and x, and let me be more consistent there. Let's just use that version of y. It all depends on what letters you're using. So if it was the letter F and L or A and R for area and radius, you would use those letters, not x and y. And also, you would interpret your n as if it was a fractional n, or if it was negative, you would actually rewrite the equation so that it would be expressed as a fractional form. So, for example, and let's just say, let's say the letters that we had were doing F and T, sure, whatever. And let's say your n value equaled negative half, and your a value was equal to 4.532, something like that. So how you would write that out as your final therefore statement is you first start off like this. F is equal to 4.532 t to the negative 1/2. But then we would interpret what this means. So then the final statement would be F is equal to 4.532 over, because the negative means reciprocal and the half means square root. So that would be over root t. Now, this is just some random thing that I just made up with some random letters, but that's what it should be. So this would be your final therefore statement in that form there. Now that we've explored the theoretical concepts of how logarithms work and how they can be used to find these relationships, it's time to actually put this into practice. And in order to do that, we need to learn how to use logarithmic graph paper. I suppose the first thing we should talk about is what logarithmic graph paper is. This is what logarithmic graph paper looks like. What you'll note is that, and we'll zoom in a little bit more here, you'll notice that the spacing decreases as our values increase. And the reason why is that logarithms, by their nature, are not linear. So in order to make the plots straight, the graph paper itself has to have this somewhat uneven scale. So the graph paper is broken up basically into quadrants. And this first quadrant represents what we refer to as a decade, or basically a power of 10. What we have here is a 2x2 cycle logarithmic piece of graph paper. You can get customized 3x3 or 2x3 or whatever. But for the purposes of what we're working with, we're just going to do a 2x2. So there is this represents one decade, powers of 10. This over here would be the second decade on the x-axis. So for example, this here, let's say that this was the ones column. So this would be 1 through 9, but then it jumps up. Then it goes 10 to 100. It's the next decade up. And the same thing applies on the y-axis. So that's the first decade, and that's the second decade. So to use the graph paper effectively, the first thing you need to do is convert your data table from the raw values, like we have here, into scientific notation. Now, just to give you a heads up here, this is the type of scientific notation that is produced by a spreadsheet. This is not the traditional notation. This is how it is done on a computer, mostly because the software finds it difficult to output superscripts and subscripts and all that jazz. So how to read this in regular scientific notation is this would be 1.00 times 10 to the 2. So that capital E represents this portion here. Now, in terms of the number of significant figures you can work with, the truth of the matter is not much. So when we look at the grid here, this is 1, this would be a 2, whatever power we have. We'll get into this in a moment. So the most you can get out of this graph is 3 significant figures. So if you had something like this here on this point, this is 1, this would be 1.1, 1.2, that's 1.3. So this is somewhere between 1.2 and 1.3. So it would be 1.2, I don't know, 6, whatever, close enough, times 10 to whatever this would be. So the max that you can get out of this type of graph paper are 3 sig figs, which means that when you're actually working with your data, you can actually round these things off to 3 sig figs because that's all you can get out of the graph paper anyway. There are limitations, but it's still very effective. Again, let's go back up to the data. So we convert everything into scientific notation. The next step is you look at what I refer to as the decades, or really the exponent on the scientific notation. Because remember, this is 1 times 10 to the 2. This 2, the 10 to the 2, represents the decade. So this would be your hundreds, because it's 10 to the 2. So for our values for F, there's only 1 decade in use, and that is the times 10 to the 2 decade. So basically everything in the hundreds, which makes sense because when we look at the force, sorry, not the force, this is actually frequency. When we look at the F column, which is frequency in this case, 100, 200, 400, 500, these are all in the 100s decade. Whereas T, which represents the period, there's a shift in the decades. Our first data point is in the times 10 to the negative 2 decade, but the rest of them are in the times 10 to the negative 3. That means the values that we put on the x-axis, because the independent variable always goes on the x-axis, is going to span over 2 decades, which is why we used this particular type of logarithmic graph paper, because there are only 2 decades to worry about for the period. So we only needed 2 cycles. So when it comes to graphing these, it always goes as follows. The x-axis, the values grow in this direction to the right. So that means towards the left here, we have the smaller values, and to the right, the larger values. So that means we start with the smallest decade first, followed by the largest one. So the next step is to label the graph paper with the appropriate decades in the right order. So let's start off with the period. Times 10 to the negative 3, that is smaller than times 10 to the negative 2. So how you read the graph paper is as follows. This right here would be 1 times 10 to the negative 3. Let's take a look at this randomly. This would be 6, well, technically 6.00 times 10 to the negative 3. All right, so what happens when we get over here? Because this 1 here seems to straddle both the first decade and the second decade. Well, here, I'll be consistent with the colors here. I'll use purple and green. So let's take a look at that. That is going to be 9.00 times 10 to the negative 3. So this would be 10 times 10 to the negative 3. Or, if we look over here, 1 times 10 to the negative 2. Because 10 times 10 to the negative 3 is the same as 1 times 10 to the negative 2. And to prove my point, 10 times 10 to the negative 3, the 10 to the negative 3 modifies the 1 column. So that's the 10 to the negative 3 column. This here would be the 10 to the negative 2 column. So this means 1 times 10 to the negative 2, which is precisely what this says here. 1 times 10 to the negative 2. So everything in this decade here would be your thousandths. Everything in this decade over here would be your hundredths. And then if we had another decade over to the right, that would be your tenths, then followed by your ones, then your tens, hundreds, thousands, so on and so forth. And of course, the exact same thing applies, zoom out a little bit here, to our y-axis. So on our y-axis, it's the same thing. So since we only have 1 decade, and that is the times 10 to the 2, the hundreds, we just put it in the first quadrant. So this up here would be times 10 to the 3. And that would be your thousands, but we don't have any data in the thousands. So this will be empty here. All the activity is going to happen in these 2 quadrants here. So the next step is plotting the points. To make this easier, I'm going to copy this chart and going to paste it down here so we can see it. So our first point is represented by this, and this is how you read it. We start off with the period, t, and then we look for where 1 times 10 to the negative 2 is. Well, that's right at that point there. And again, how you read it, that's 1. Perhaps let's use a different color for highlighting. We'll do red. So that's 1 times 10 to the negative 2. So that's this right here. Now, of course, we have to find the corresponding y component. Well, that's going to be 1 times 10 to the positive 2. Well, when we move over here to the y-axis, this whole decade is the times 10 to the 2. So the very first point is the 1 times 10 to the positive 2. So that right there is your 1 times 10 to the 2, which is why our point is located right there. Focusing on the second point. So we start with our x-axis, well, technically t in this case, but it's on the x-axis, and we're focusing on this value here. So now we're in the 10 to the negative 3 decade. So we're going to locate 5 times 10 to the negative 3. This is the 10 to the negative 3 decade, and there is the 5. So I'm just going to put a little hash mark right there. Next step, we find where the y-axis or the dependent variable position is. And that's going to be 2 times 10 to the 2. So when we go across, again, the whole decade is 10 to the positive 2, and the 2 times 10 to the 2 is right there. So if we extrapolate, that's where the 2 points meet. I should say that's where the coordinate meets, the x component and the y component of our coordinate, right at that point right there. And then you repeat for the rest of them. Personally, when I'm graphing with logarithmic graph paper, I do find it more convenient to actually draw a light line from where the positions are. I find it sometimes hard to follow up with my hand. So what I will do is I will do exactly what I did with that last example, is I'll start off and identify the first point. So 2.5 times 10 to the negative 3. So zooming in here. So that's 2.1, 2, 3, 4, 5. And then, now when you're doing this with actual real life graph paper, best practices would be to use a very lightly drawn pencil line so you could erase it later. So this line represents, and let's keep it red, a little easier to see. This is the x coordinate of our point. Then we follow up with our y position, which is 4 times 10 to the 2. Then with my ruler, I sketch another light line. And of course, where the 2 lines intersect is where our point is located. So then you draw your point, and then you would erase these lines to remove the clutter from your plot. And then so on and so forth. So here are the 4 points drawn on. And as you can see, they fall perfectly in a straight line. And that will always happen. That will always happen if there is a fixed relationship in the data. No matter how weird the relationship is, provided that the nature of the relationship does not change during the data set. So for example, that it doesn't go from a squared relationship to a cubed relationship, as long as it doesn't do that, and there aren't too many phenomenons in nature that I know of that would ever do that, provided it is the same power, you will always get a straight line, no matter what that power is. So whether it is something to the squared, cubed, cube root, negative cube root, whatever, it will always produce, always produce some kind of straight line. The next step would be then to draw a line of best fit. In this particular case, my data was obviously pretty perfect. All the points line up exactly together. That is not always going to happen. So when you have to do this in real life with real data, you're going to have to draw your line of best fit. One thing that's important to remember about a line of best fit, it's not just about getting equal numbers of points above and below. It is equally as important to follow the trend in the data. Occasionally, you're going to get a rogue point. So let's say for the sake of argument, I'll just draw in a couple of random other points. So let's say we had a point there, one there, one there. And then let's say we had one that was like way out in left field. Under these circumstances, you would actually ignore that point when making your line of best fit. This one is very much an outlier and isn't following the general trend. So it is best practices to avoid trying to integrate that one with the fold. Because if you're trying to get it so that it sort of splits the middle, the tendency is that you might want to do something like this. It's like, oh, okay, well, because that one's lower, you might want to change the angle a little bit to sort of balance it. You know, it's like, oh, maybe that's a little bit more balanced because this one's so far off and these little ones being a little off are equal to the amount that this is off. That's wrong-headed, and that's not the technique. The technique would be to ignore the obvious outlier. Of course, you would try to go back to the data and see why that particular point was an outlier. If you did just something fundamentally wrong when you collected the data, or possibly there would have been a miscalculation. So you should still investigate to see what happened with that point. But when it comes time to making the line of best fit, you would ignore it. Okay, so now that we got the line of best fit, this is where the magic happens. So again, we are looking at equations that are going to be in this form here. And that is y equals ax to the n. So what we're focusing on right now is finding n. Then once we have the value for n, we then solve for a. Before we begin, we need to pick 3 points that are on the line of best fit. In this case, all 3 points are there. So we could use these 3 points that are visible here. I will call this point A, and then you have to put in its coordinates. Now, you don't actually have to put the scientific notation values in. You can actually use the raw values if you like, if they're easier to work with. So the green point, that was the 2 to the negative 3, and that would be 5 times 10 to the 2. So you could use 0.002 and 500, or if you prefer, the scientific notation, 6 of one, half dozen of the other. So I'll just do the scientific notation. Now we know that it's 3 sig figs, but for the interim calculations, you don't have to carry all of the sig figs. You just have to make sure that the final answer is rounded off to the appropriate number of sig figs. So now point B, 2.5 times 10 to the negative 3 and 4 times 10 to the 2. And finally, our point C, that's 5 times 10 to the negative 3, 2 times 10 to the 2. Now we calculate the value for n using that slope type calculation. Off to the side here, we'll do this calculation. So we're going to find n using points B and C. Actually, I'll be lazy. I'm just going to copy and paste this and need to change the font to black. And of course, point C, paste that, and there we go. When you're doing your slope calculation, it doesn't matter which one is your first point or your second one. You just have to be consistent. So arbitrarily, we could say B is our first point. So that would be x1, y1, and C would be our second point, x2, y2. It doesn't matter as long as you keep the order, whatever order you choose, you have to keep it. And the biggest mistake that students make is they will flip the order of their x1, x2, and their y1 and y2. The formula, oops, look at that. I always want to go to slope. It's not slope, it's n, but it looks like the slope formula. And remember, slope is delta y over delta x. The logarithmic slope is just going to be log delta y, which is y2 minus log y1 over log x2 minus log x1. This form is the easier form to remember it because it's just the slope formula, but it's not the easiest form to calculate. The easier form to calculate is actually using the quotient rule to rewrite the side. You don't have to do that. You could just substitute the numbers in here and you get your results. But if you want to make it a little faster on your calculator, this numerator is reduced to this log of y2 divided by y1 over log x2 over x1. One thing to note, log isn't usually capitalized This is just a bad habit of mine because my L's start to look like ones. As a result, I tend to use a capital L to avoid that problem. Substituting in. So we've got 2 times 10 to the 2. That's our y2 over our y1, which is 4 times 10 to the 2, all over log our x2, which is 5 times 10 to the negative 3, divided by our 2.5 times 10 to the negative 3. One advantage of keeping it in scientific notation is this little convenient thing happens here, and this little convenient thing happens down there. Our equation now simplifies to log of 0.5 over log of 2, which gives us a value of negative 1. Therefore, n is equal to negative 1. Again, this is a prime example. I guess I don't have to do a fancy one. I'll just do this. Negative 1. There we go. Because the data we had in this case was absurdly perfect, we didn't get any weird decimal places. But if you do get a weird decimal place, you round it off to the closest one of those predetermined values. And those predetermined values were as follows. So n can either be equal to plus or minus 1, 2, 3, 4, etc., or plus or minus 1/2, 1/3, 1/4, etc., etc. So more realistically, if this was an actual experiment, this negative 1 might have been closer to something like, I don't know, let's say you got negative 0.1002. Oh, what am I doing? Let's try that again. Negative 1.010023, something like that. When you see something like this, the closest thing that resembles any of these would be, of course, the negative 1. Same thing if you got something like this, negative 0.99921, whatever. Again, the closest would be to the negative 1. And that is what you round it off to. You always round it off to one of these values here. And for the next step, you work with the rounded value for n, not the original, but the rounded one. Now we have the value for n. The next steps are to calculate the value for a. And as a reminder, you calculate the value for a 3 times using those 3 points. First, we're going to find a1 using our point A, which was 2 to the negative 3, clean that up a bit, and 5 times 10 to the 2. Just double checking, 2 times 10 to the negative 3, 5 times 10 to the 2, we're golden. Starting with the general formula, y, there I am with that cursive y again, y equals ax to the n. But now we know n is negative 1, so we can actually put in times 10 to the negative 1. What we're going to now do, in the interest of making the algebra easier, I'm going to rewrite this as y equals a over x, because x to the negative 1 is just the reciprocal. Isolating for a, this becomes just x times y equals a. So this is our general formula. We'll turn it around. A equals x, y. Now to actually find a1. a1 is equal to x1 times y1. 2 to the negative 3 times 5 times 10 to the 2, and we get exactly 1. But based off the fact that we have the sig figs, 1.00. And we repeat for points B and C. Put my little comma in there, and there's our A3. We don't have to start from this point here. We can work with this arrangement of the formula here. A2 is equal to x2 times y2. That's 2.5 times 10 to the negative 3 times 4 times 10 to the 2. And we get 1 again, but rounding off to 3 sig figs. And let's not confuse our subscripts there. There we go. And lo and behold, we get the same thing for A3 and right A3. There we go. Now, it seems kind of silly to do this next point in this particular question because obviously the average of A1, A2, A3 is going to be 1. But the whole point is to show you the process in any situation because it's not going to work out exactly like this with real data. So to find A is equal to A1 plus A2 plus A3 divided by 3. I don't usually carry the extra sig figs during the calculation part, just as long as in the final value, you have the correct number of sig figs written. So we get A is equal to 1. Therefore, now we can complete our equation. Y, I just can't help myself apparently. Y is equal to 1.00 x to the negative 1. But I don't want you to leave it like this. I want you to do it like this, or y is equal to 1 over x, except I did one thing that was goofy. And I just realized what silly mistake I made. F and t. So it's okay, I suppose, that we used the x and y here, but it should have been f and t. So we have to fix this. All right, let's start from scratch. F, there we go, is equal to 1.00 t to the negative 1, or f is equal to 1.00 over t. And just so you know, the actual formula that this comes from was frequency is equal to the reciprocal of the period. I just threw you off the trail by using a capital F instead of a small f, but this data was actually just generated using the relationship between frequency and period. So there you have it. Now you have the technique to find these relationships in the data, but not just the proportional power, because in grade 11, all we could find was how the dependent and independent were related using a proportionality. Now, using the logarithmic method, we can actually get an explicit equation. So not just a proportionality, but the actual equation. And this is pretty powerful, very useful stuff. The next step, of course, is to apply what we just learned here on the data we got for this particular lab that we did frequency versus length. Now that you know how to do it, go do it.